welcome to this lecture. In this lecture, we are trying to explain you the shell and tube design approach in details. You may remember in the last class, in the last lecture, we have talked about the shell and tube heat exchanger design approach, and here with an example we will try to elaborate the same. Now, just to recapitulate what we have talked in the last class, first of all we need to define the problem, like what is the problem definition, what are the constraints, what are the desired outputs, and based on that, if we have all these informations with us, we have to first select the type of exchanger that we are planning to design. So, we will select the type of exchanger we are going to design. Now, for this case it is already fixed and we have decided this is the shell and tube type. Now, once we have decided the heat exchanger type, we now need to establish certain design parameters, like what would be the expected heat transfer coefficient for a typical heat exchangers like shell and tube for a different kind of fluids. So, once we have that knowledge with us, we will be able to find out using the epsilon NTU or the other techniques that we have learned in the earlier classes. So, basically we will be able to find out some of the parameters or design parameters. So, design parameters, by saying that, we mean to say that we come to know about the length, maybe we come to know about the diameter of the tube, we will be able to tell about the shell diameter, etc. So, once we know all those parameters, then what we do is that now we go for a rating problem. Till now we were trying to solve, up to this part we were trying to solve a sizing problem, that means where all the inlet and flow conditions and the exit flow conditions, temperature, flow rate, etc. are known, and we try to estimate the heat exchanger length or the heat exchanger size, etc., etc. So, this was what was the sizing problem as we have learned in the earlier class. So, this was basically we are trying to solve a sizing problem in this one, but up to this part we will try to get a rough estimate of the sizing problem. Now, once we know the rough estimate of the design, then we go for the rating problem. What is rating problem? Now, as if we have the geometry of the exchanger known, the inlet and of the two streams are known, and when we know the inlet condition of both the fluid streams and the heat exchanger configuration is known, we can find out what is happening to the exit fluid streams, or rather we try to find out the performance of the heat exchanger. If we find that the heat exchanger performance is acceptable, like what is the pressure, what is the heat load, etc., that we have defined earlier in the first problem definition, it is comparable with or it is acceptable to our problem definition or no, or then accordingly we will go for the mechanical design. If we find that it is not in accordance to our desired output or what we intend to do, then we have to make a change in the estimation. So, basically you can understand that this is a kind of trial and error. So, we are starting with an initial rough design and we are trying to rectify that one according to our need. So, let us try to solve this one with a small example. Here in this problem definition, this is, as you can understand, this is a single cell, single tube heat exchanger. Here these are the baffles, and we have these are the baffles, these are the baffles, and one fluid is entering, the condensed water is entering on this side, and it will be flowing like, I am sorry, this is supposed to, this is not a good design. So, it is supposed to come from this end, and it should come like this, and it is supposed to come, another baffle should be there. So, it should come out from here. So, now on the other side, the raw water is coming and it is flowing like this, and finally, it will flow like this from this outlet. So, here what are the conditions or the problem definition that is given? The raw water, this is entering at 17 degree centigrade, and its Cp is also given, it is 4184 joule per kg Kelvin, and its flow rate is also known, this is 30,000 kg per hour. So, we know the flow rate of this water, and we know the inlet temperature of this raw water. What is about the condensed water? It is entering at 67 degree centigrade, 67 degree centigrade, and at 0.2 bar. Now, its flow rate has been specified as 50,000 kg per hour. Now, we know the inlet temperature of the raw water, we know the inlet temperature of the condensed water. What is expected that we have to design a shell and tube heat exchanger where the exit temperature would be 40 degree. So, this raw water is supposed to come out at 40 degree centigrade. It should not be less than 40 degree. So, this raw water is going to get heated up, and it will be heated up by the condensed water, and its flow rate and its inlet temperature is given. And what we intend to do is that the raw water should always be, it should not be any time less than 40 degree centigrade. Now, what are the other conditions that has been already specified? Let us look into that. It has been said that it should be a shell and tube, and it should be a single cell and single tube pass, not necessarily also, I mean, but preferred is single tube pass, and coolant velocity is maximum 1.5 meter per second, that is the maximum allowable velocity. There is some kind of foul resistance, or that means there is a possibility that over the time it will accumulate some kind of scale, and that resistance, that foul resistance will be, that foul resistance is equals to 0.000, then 176, its unit would be meter square Kelvin per watt, just inverse of what we get for the heat transfer coefficient. Now, this is the foul coefficient and foul resistance, and the tube length of this heat exchanger, that has already been specified because of the length constant or space constant. It cannot be more than 5 meter. So, we will work with 5 meter maximum length. What it has been said is the tube material, these tube materials are made of carbon steel, so that we know the thermal conductivity. So, it becomes K equals to 60 watt per meter Kelvin. Now, the tube diameter also has been specified. So, the tube diameter is also specified, and it is basically OD is 19 mm and the ID, that is equals to 16 mm. The tube arrangement, that means how are we going to arrange the tubes. This is the tube sheet. In the tube sheet, they will be arranged in the square pitch. So, that means it will be inline flow, and this is how they are going to be arranged. This is the 4 tubes. If we look at, the flow is taking place like this, and this is the minimum area. We have already learned about it. So, this tube arrangement has already been said. It is square pitch, and the pitch ratio, that is pitch ratio PR, that is PT by D0, where D0 is the outside diameter and this is PT. So, that PT by D0 is equals to 1.25. So, this has already been specified, and there is also the baffle spacing. The baffle spacing is 0.6 of the cell diameter. And it is baffle cut is 25%, there is baffle cut. So, if we look into this total baffle, 25%, this part is 25% of the total one. And as we have said that there is a possibility that there would be formation of scale. So, what we need to anticipate that over the years it will accumulate some kind of foul, I mean the darts on it and scale on it. So, accordingly we have to slightly over design the heat exchanger, and it should never be more than 35%. So, that we have to take it into account, that considering the fall resistance, our design should never be more than 35% of more over designed. So, these are the specification which is given. Now, we have to look for the actual sizing of the shell and tube. So, how do we do? So, what we need to keep it in mind, that we have to take an approach as we have discussed in the previous schematic. This is the flow chart we have shown. So, we will start with, this is the problem definition has already been told. Now, we have to already, it is also selected. Now, we will try to make an rough estimation of the design parameters, like we will try to find out what would be the number of tubes on the shell side, what would be the diameter of the shell side. And once we know that, we will come back to this rating problem. So, let us try to look into that, and we have this kind of heat exchanger. So, now we will start the calculation. So, we know that the heat transfer, the flow rate of the cold fluid, CPC the specific heat of the cold fluid multiplied by the difference in temperature. So, if we look at all this temperature, all these parameters are known on the right hand side, so that we would be able to find out the amount of heat transfer. So, this is just nothing but, if you try to calculate, this is 30,000 divided by 3600 multiplied by 4179 is the Cp, and then you have the difference in temperature 14 minus 40 minus 17, 40 is the desired temperature and this is 17 is the inlet temperature of the cold fluid. So, it is coming to be 801 kilowatt amount of heat that is going to be transferred, and this is equal to obviously m dot h Cph Thi minus Th0. So, here this equation will be used to find out the exit temperature of the hot fluid, and if we look at this will come out to be, because already we have calculated Q equals to 801, and if we put that value we will be able to estimate it to be 53.2 degrees centigrade. So, now you see already we know the all inlet and exit temperature of the heat exchanger. So, now at this point we have to make some kind of assumption regarding the heat transfer coefficient, and so that we can try to estimate the overall heat transfer coefficient on the shell side. So, how do we do that? In order to do that, we have to depend on certain realistic values of the internal and the external heat transfer coefficient. So, this is the overall heat transfer coefficient, where we find this is the wall resistance, this is the fouling resistance inside and at the outside. Then we have the overall resistance of the external one, and this is the overall heat transfer coefficient on the inverse of the overall heat transfer coefficient. This is 1 by U0 A0. So, this is what we get in general, and for this specific case where we have R0 and Ri as the radius of the two tubes, we have 1 by H0, then we have R0 by Ri. This is defined in terms of the external heat transfer area. So, this is the what is called the fouling resistance. This is already been given. This takes account of the heat transfer resistance offered by the wall of the tube, and here this is we have taken a rough estimate of this cell site heat transfer coefficient to be 500 watt per meter square Kelvin, and we have taken it as 4000 watt per meter square Kelvin. This has been taken from the heat exchanger selection by S. Kakak et al. So, they have given a chart of these values which are typically which can be considered for different kind of fluids and different kind of heat exchanger configuration. So, based on this value, if we now estimate, we will find that already we know H0, if we can substitute R0 already we have talked about, R0 is already known to us, this is, and this is R0 is, say if we define it in terms of, this can also be D0 by Di. So, D0 is basically D0 is equals to 19 mm and Di is 16 mm. Hi is already given, Rfi is already known, that is equals to 0.000176 meter square Kelvin per watt, and we have D0 or sorry R0, and you have to put the value of K and R0 by Ri and Ln. So, if we put all these values, we will find UF, this UF where we consider the fouling resistance. This comes out to be 1428.4 watt per meter square Kelvin. Now, we also try to find out if it is a clean surface. That means, if there is no resistance given or offered by the fouling. So, in that case what will happen? We will find that this term is not there. In that case, we define it. Let us look into that condition. Here in this case, as you can see that this part is not there. So, when this part is not there, corresponding R value is not appearing here, and in this case all the other parameters being known, we can try to find out UC, and this will come out to be 1908.09 watt per meter square Kelvin. So, you can understand that this is in contrary to or in contrast to our earlier value where we were considering the fouling resistance, and that was appearing 1428.4 watt per meter square Kelvin. So, this resistance, or I am sorry, not this, this is the fouling resistance. This fouling resistance contribute, I mean we are considering, when we are considering the fouling resistance, we are finding that the heat transfer, overall heat transfer coefficient is substantially small as compared to the clean heat exchanger. So, now we will try to find out, based on this information we have already have the knowledge about the overall heat transfer coefficient, then we have the knowledge about the heat transfer. So, next is we have the knowledge of the overall temperature profile, or rather the exit and inlet temperature. So, we will be able to find out what is the log mean temperature difference if the fluids are arranged in a counter current exchanger configuration. So, if we look into it, we will find that the hot fluid is coming from 67 degree centigrade, and it is coming degree centigrade, it is coming to 53.2, whereas the cold fluid is entering from 17 degree centigrade, and it is coming out at 40 degree centigrade. So, now we can find out the delta T1 and delta T2, and we will find that this difference and this difference will be appearing in this expression to give us a delta T ln of, we will be able to find out this one. This will come out, if you put all these values, you will find that this is coming as 31.4 degree centigrade as the delta T log mean. So, in reality this is true only for the purely counter current exchanger, but in reality it is not so. So, this is 31.4 degree centigrade, and we are assuming a correction factor of 0.9. So, this we have already learned that for a cross flow type, or if when we have a single pass, single tube heat exchanger, single cell, what would be the corresponding correction factor, but we are just assuming it at this moment. This assumption has to be later on rectified. So, this is an assumption, and based on that assumption we are now trying to find out the, if we now look, we have the knowledge of Q, we have the knowledge of delta T m, we have the knowledge of U f, and we have assumed a correction factor. So, accordingly we would be able to calculate the A f corresponding to the overall heat transfer coefficient, where this is considering the fouling, and here this is where we have not considered the fouling, and this is basically a clean heat exchanger. So, accordingly we will be able to find out another heat transfer surface area, and obviously as you can understand that this will be higher than this one. So, now we will try to estimate this one, and you will find that this is coming to be 20.05 meter square, whereas the other one will come to be 15 point, if you put all these values, meter square. So, the Q remains same, the delta T, L and F remains same, and only thing is changing is U f and U c, that is giving rise to different kind of overall area, which is to be taken into consideration for the heat exchanger calculation. Now, once we know this heat transfer surface area which is necessary, and obviously we will be going by this surface area which corresponds to 20.05 meter square. So, our calculation will be based upon this one, because eventually we find that the fouling is going to occur, and this fouling is going to be there, so that if we do not take that extra area, the desired performance of the exchanger cannot be expected after certain time. So, now if we look into the area of this A f by A c, so this is what is the clean surface area, and this is anticipating some kind of fouling. What is this ratio? This comes out to be 1.34. So, now if you look at that, we have been told that the over design should be less than 35%. So, as we can understand that this is less than 1.35. So, this design is or this oversizing is within the limit. Thank you.